Hello AP Physics, this is Dr. Brenzi and this is lesson 9.1.4. Our objective in this lesson is that we're going to be able to determine if it takes more heat to raise the temperature of a gas or solid and explain why that is true. In order to do that, I need to introduce a concept to you called specific heat. Specific heat is the amount of heat required to raise the temperature of a kilogram of material by 1 degree Celsius. So here's basically a mathematical explanation of that. It says specific heat, that's what this is. Whoops. Oh, I forgot to mention. Well, I'll mention that. But anyway, the specific heat is the amount of heat it requires to raise the temperature by a certain amount. And that has to also be divided by the mass of the material, and that's how you find specific heat. If you don't make the temperature change very drastic, then actually you can assume that specific heat is constant as a function of temperature, and then you can say that the amount of heat that you have to put in will change the temperature by this much, and this is the relationship between the two. M is the mass of your material in kilograms. And before I go on to the next slide, another name that will be often given to this specific heat is what's called heat capacity. So if you're doing some Google searches or anything like that and wanted more information about this, you can also look up heat capacity. All right, so there is also another very common term, and that's called molar specific heat. And the only difference between this and the specific heat that we looked at on the previous slide is that now we are talking about the amount of heat required to raise the temperature of a mole of material instead of a kilogram of material. Usually this molar specific heat is given by a capital C instead of a small c. Otherwise it works very similarly to what I had on the previous slide. N, by the way, is the number of moles. And there is a relationship between molar specific heat and specific heat that's given by this equation, and this M is molar mass, that's the amount of mass in 1 mole, and N is your number of moles. Very often we measure the specific heat of materials by conducting experiments, and there are 2 ways in which to measure specific heat. One is that when you are keeping the volume constant, and the other is when you're keeping the pressure constant. Keeping the volume constant is usually the way that gases are measured as far as their specific heat. And the reason being is because it's a lot easier to keep a gas at a constant volume. You build a box and you make sure that box cannot flex over the pressures that you're going to be dealing with. So you build a box, you stick your gas in there, and then you stick a thermometer into it, and you have a heating element of some sort, and you have it well regulated. In other words, you understand very well how much heat it's outputting as an amount of current goes to this wire, and that is what that's how you actually measure specific heat. Another reason why you want constant volume for a gas is because if you're measuring specific heat, you want all of the heat that you're inputting to go into the temperature of the gas. If this box expands or is allowed to expand, then some of that heat that you are inputting is actually being converted to doing work on the outside surroundings, in other words, to doing work on the box. You don't want that when you're trying to measure specific heat, so you want to actually measure this at constant volume. On the other hand, when you're measuring solids or liquids, you usually use a specific heat at constant pressure, or that's what you end up measuring, because it's a lot easier to keep a solid piece of metal at a constant pressure of 1 atmosphere or 100 kilopascals or whatever pressure you want to look at than it is to actually try to keep this rod at a constant volume, because we have thermal expansion, right? And thermal expansion can cause this volume to expand in turn, and that means that we would have to keep this from actually expanding when we change the temperature, and that would be difficult to do. So usually solids are measured with pressure being constant. You might be wondering to yourself, Dr. Berenzi, when do I use CV and when do I use CP? Well, if you're dealing with an environment where your pressure is being kept constant, you want to use CP. And that usually means solids. So if you're heating up a solid and it's just sitting there, you're going to want to use CP, the specific heat constant pressure. On the other hand, if you're measuring a gas in a box, you're figuring out how much heat you have to put in a gas in a box in order to raise it so many degrees Kelvin, or so many Kelvin, then you would use CV, the specific heat at constant volume. Okay, now let's go from the real material to ideal situations so that we can understand the physics behind this thing. Let's think about a monatomic ideal gas. So it's an ideal gas that just has one atom per molecule, and we know that it obeys the ideal gas law. And I'm going to go back to the nRT form instead of the capital NKT form. And when I do that, I can also say that the amount of kinetic energy stored in this gas is equal to 3/2 times little n big R times T. We learned this in lesson 9.1.1, but we had a capital N little k here. Well, hopefully I can convince you really quickly that this ideal gas law I can put as either this or I can put as capital N little k. So anytime I have capital N little k, I can replace it with little n big R. Those two products equal the same thing. So I can replace capital N little k with little n big R. And that's what I did. Okay, so if I change the temperature by a small amount, an infinitesimal amount dt, I am going to correspondingly change the kinetic energy by a small amount, and that's given by this relationship right here. I also know that the amount of heat that I put into the gas is given by this equation right here. All the heat that I put into this gas is going to go into raising its kinetic energy, which means that dq is equal to dke, which means this is equal to this. And when I set those two equal and do some algebra, I figure out that the specific molar heat at constant volume is equal to 3/2 times R. And R is this constant in the ideal gas law. Well, this number turns out to be 12.47 joules per mole per Kelvin. So a monatomic ideal gas, you would need 12.47 joules in order to raise a mole of gas by 1 degree Kelvin. Oh, I keep on saying that. 1 Kelvin. There we go. I got to get myself out of that habit. Okay, so that's a monatomic ideal gas. What about a diatomic ideal gas? Because there are a lot of gases out there that are diatomic, like oxygen and nitrogen. Both of those come in diatomic gas form, which means you have 2 atoms for every molecule instead of 1, and that changes the game a little bit. I'm not going to go through a complete derivation, but when we were dealing with a monatomic gas, remember we had 3 translational directions that this molecule can move. It can move left, right, it can move up, down, and it can move in and out of your monitor. Well, when you have a diatomic gas, you also have two possible ways that this can rotate. It can either rotate in a circle like this, or it can rotate in a circle that actually comes in and out of your monitor. And you could imagine it's a very similar circle, except it's you would be looking at it from the side up and down rather than looking at it from the top like this. So it's hard to help you visualize that with just a pointer and some talking, but hopefully you get the picture. Well, anyway, whether you get the picture or not, there are two ways that this thing can rotate, which means it has 5 degrees of freedom in its motion. Why is that important? Well, each of those degrees of freedom has an energy equal to 1/2 nRT. So if you add all those up, that's 5/2 nRT. And this 5 comes from the number of degrees of freedom. Remember, for a monatomic gas, we had 3/2. Well, now we have 2 extra degrees of freedom, so now we have 5/2 nRT. Well, just like on the last slide, we can use this, and we can use the ideal gas law to show that the specific heat at constant volume, specific molar heat, has to equal 5/2 times R, and that is equal to 20.79 joules per mole per Kelvin. That means that it takes 20.79 joules to heat up a mole of this gas by 1 Kelvin, as opposed to a monatomic gas where we only needed 12.49 joules per mole per Kelvin. So it's going to be harder. It's going to require more heat to heat up this diatomic gas by a Kelvin than it will be to heat up the monatomic gas. Well, how well do these ideal laws work? These ideal relationships for specific molar heat. Well, it turns out that if you actually look at some measurements, these monatomic gases, which are in black here, actually do a very good approximation to this molar specific heat that we just calculated for a monatomic ideal gas. So they behave pretty similarly to an ideal gas. The diatomic molecules, like hydrogen, HCl, hydrochloric acid, nitrogen, nitrous oxide, and oxygen, those behave pretty similar to a diatomic ideal gas, but you can see that some of them are starting to get higher than that. Now, I'm not an expert in this field, but I get the feeling I understand why. Because there actually is another degree of freedom that we did not look at for a diatomic molecule. You could actually think of a diatomic molecule as 2 masses connected by a spring. And this spring is the intermolecular bond between these two atoms, interatomic bond, This thing can vibrate, okay? It can bounce like a spring. Now, quantum mechanics locks this spring or makes it extremely stiff, especially for these lower, especially for those lighter elements. But once we start getting heavier elements, they start to make this vibration a little bit easier to happen. So that means that some of our heat energy actually has to go into this vibration, which means that we're going to get more degrees of freedom, which means this is going to go up. So I'm thinking that's what's happening with chlorine here, and maybe even hydrochloric acid. But again, I'm no expert, so maybe there's a different explanation. I don't know. Oops. All right. Let's talk about one last thing here, and let's talk about, whoa, hey. All right, I'm just going to let it write. An ideal crystal. So a crystal is a lattice. It's a regular pattern of atoms, And you can think of those atoms connected together, bonded together with other atoms nearby. And you can think of those interatomic bonds as springs. And if the vibration isn't too heavy, you can actually think of these as springs that obey Hooke's law. In other words, force is equal to negative kx. Well, if you can do that, then as soon as one of these atoms starts moving, and it starts moving in any direction, well, not only are you going to have kinetic energy from that motion, but you are also storing up potential energy in this interatomic bond. That means that not only are there 3 possible degrees of kinetic energy, but there has to be the same amount of potential energy. Now, to convince you of that, I can take you back to a mass on a spring. If we plotted energy versus time for a mass on a spring, we know that the kinetic energy might do something like this. It might go up to its maximum total energy, come back down to 0, go back up to its maximum total energy, and go back down to 0. The potential energy is 180 degrees out of phase with that. Now, on average, both of these share half of the total energy. So whatever kinetic energy I have on average is going to be the same amount of potential energy I have, which means that the total energy that I have in this lattice, in this crystal, is 3 times nRT. Well, that means that the specific molar heat, or the molar specific heat, is equal to 3 times R, which is 24.9 joules per mole per Kelvin. And this discovery was made by a couple of scientists, Dulong and Petit. And so we call this rule right here for an ideal crystal the rule of Dulong and Petit. Well, the last thing I have to answer for you before I leave is, okay, does it take more heat to heat up a mole of this crystal, or does it take more heat to heat up a gas? That was our question in the beginning, in the opening slide, and I'm going to leave it up to you to figure that out. So I'll look forward to seeing your answers tomorrow, and look forward to talking more about ideal crystals and specific heat. All right, bye.